Welcome to Quantum, a channel dedicated to theoretical physics, with all its rigorous mathematical underpinnings and profound philosophical implications.
Welcome to Quantum, and to the first lecture in our new series on gauge-gravity duality and matrix quantum mechanics. In this series, we explore how string theory and quantum field theory converge in the context of Dp-branes, holography, and matrix quantum mechanical models. Today's lecture lays the foundation by introducing the central object of interest, the Dp-brane. First, we begin with the boundary conditions of Dp-branes. We'll examine how open strings can end on extended hypersurfaces in spacetime and how this gives rise to Neumann and Dirichlet boundary conditions. These conditions define what a Dp-brane is, an object on which open strings can end, with p spatial dimensions. Next, we move to quantum open strings in the presence of Dp-branes. Quantizing open strings leads to a rich spectrum of excitations, including gauge fields and scalar fields localized on the brane. These are the degrees of freedom that describe the low-energy dynamics of D-branes. We then study open strings stretched between multiple Dp-branes. When two or more Dp-branes are present, open strings can stretch between them. We'll analyze how this leads to a matrix-valued field content and a non-Abelian gauge structure on the brane world volume. After that, we examine the spectrum of superstring theory. We review the Neveu-Schwarz and Raman sectors, the role of the GSO projection, and how D-branes couple to fields in the Raman-Rahn sector, providing the link between open and closed strings. We then focus on the NS to NS magnetic field and string charge. The Kalb-Raman field plays a role similar to a magnetic field for strings. We'll see how strings act as sources for this field and how their conserved charge leads to a topological notion known as string number. In the next section, we study gauge invariance and Raman-Raman charges. We explain how the gauge field on the Dp-brane must be coupled to the Kalb-Raman field in a specific way to preserve gauge invariance, and how D-branes carry electric charges for higher form RR fields. We then introduce the Born-Infeld action. This is the nonlinear extension of Maxwell theory that governs the gauge dynamics on a single Dp-brane. It naturally incorporates a maximal electric field and appears in the low-energy effective action. Afterward, we examine the Chern-Simons action. This term describes the coupling of Dp-branes to the Raman-Raman potentials. It reveals the topological and magnetic structure of the theory and accounts for lower and higher rank RR interactions. Finally, we turn to the non-Abelian extensions. For multiple Dp-branes, the gauge theory becomes non-Abelian. We discuss how the Born-Infeld and Chern-Simons actions are generalized when fields become matrix-valued, and how this leads to new physical effects such as brane polarization. This first lecture sets the stage for the deeper themes of gauge-gravity duality, where D-branes act as bridges between open-string gauge theories and closed-string gravity. Let's begin. Boundary conditions of Dp-branes. In string theory, the motion of a string through spacetime is described by a set of coordinates that depend on two parameters, tau, representing time, and sigma, representing the position along the string. For an open string, sigma ranges from 0 to pi. Tau spans all real values, tracing the evolution of the string. These spacetime coordinates are denoted by x mu, and they describe how the string embeds itself in a higher dimensional spacetime. The dynamics of the string are governed by what is known as the Polyakov action. It involves the spacetime metric, the worldsheet metric, and the derivatives of the string coordinates with respect to both tau and sigma. When we vary this action to derive equations of motion, boundary terms arise. For the theory to be consistent, these terms must vanish. This can happen in different ways, depending on the type of string. If the variation of the string vanishes at both endpoints, that is, if the derivative with respect to sigma is 0, then we are dealing with Neumann boundary conditions. This is the case for open strings, where the endpoints are free to move. On the other hand, if the string coordinates themselves are periodic, we get closed strings. These have no endpoints and loop back on themselves. There's also a third possibility. The boundary term vanishes if the string ends on an extended object in spacetime, a Dp-brane. In this case, some coordinates obey Neumann conditions, allowing movement along the brane, while others obey Dirichlet conditions, pinning the endpoints at fixed positions orthogonal to the brane. A Dp-brane is an object with p spatial dimensions. It is defined by fixing the coordinates transverse to its world volume at constant values. The coordinates parallel to the brane remain free, allowing the string to vibrate along those directions. Thus, the open string splits into two distinct sets of spacetime coordinates. The first set, labeled x superscript m, corresponds to directions along the Dp-brane. These satisfy Neumann boundary conditions, meaning the string's endpoints are free to move along these dimensions. The index m runs from 0 to p, covering the time direction and all p spatial directions of the brane's world volume. The second set, labeled x superscript a, corresponds to directions transverse to the brane. These obey Dirichlet boundary conditions, meaning the endpoints are fixed at specific positions in space. The index a runs from p plus 1 to d, where d is the total number of spacetime dimensions minus 1. These mixed boundary conditions are not just consistent with the theory, they actually require the existence of Dp-branes as physical objects. Quantum open strings in the presence of Dp-branes. When we quantize open strings in the presence of a Dp-brane, we find that the resulting spectrum contains three kinds of fields. First, a tachyon field, which is typically a sign of instability. Second, a gauge field defined on the brane's world volume. This is a U1 gauge field with components labeled AM, where the index m runs over the p spatial directions of the brane, plus time, p plus 1 dimensions in total. And third, we have normal scalar fields labeled XA, corresponding to the directions transverse to the brane. There are d minus p such directions. All of these fields are localized on the Dp-brane. In other words, they live entirely within its world volume, which is a p plus 1 dimensional slice of the full spacetime. The scalar fields, both the tachyon and the normal coordinates, transform as scalars under Lorentz transformations in the brane's world volume. Meanwhile, the gauge field AM transforms as a vector and has p-1 independent polarizations due to U1 gauge invariance. So altogether, we have p-1 tangent gauge fields and d-p scalar fields. These give us a total of d-1 massless physical states. In the special case where p equals 25, meaning a d25 brane, the open string sees the full 26-dimensional bosonic spacetime. There are no transverse directions, so there are no scalar fields. The d25 brane is fully space-filling and cannot be displaced. For lower dimensional branes, however, displacements are possible. These are captured precisely by the normal scalar fields XA, which describe how the brane can move in the higher dimensional spacetime. In type 1 superstring theory, the same spectrum appears, but the tachyon is absent. Only the massless fields remain, the gauge field and the scalar fields. Finally, the critical dimension remains unchanged. For bosonic strings, it's 26 dimensions. For supersymmetric strings, it's 10. Open strings ending on N, coincident Dp-branes. Let us now consider open strings stretched between two parallel Dp-branes. These branes are located at fixed positions in the transverse directions. The first brane sits at a position we'll call x bar 1, and the second at x bar 2, both defined in the directions orthogonal to the brane's world volume. In this setup, open strings fall into four distinct sectors. Two of them, called the 1-1 and 2-2 sectors, represent strings that begin and end on the same brane. These have already been discussed. The remaining two, labeled 1-2 and 2-1, represent strings stretched between the two branes. These sectors are labeled using Chan-Paton indices, which keep track of the string's endpoints. For a string going from brane 1 to brane 2, the Dirichlet boundary conditions fix the endpoints at their respective transverse positions. This results in a stretched configuration. The energy of such a string depends on the distance between the branes. Its spectrum includes a tachyon-like state, a set of massive scalar fields corresponding to transverse vibrations, and a set of massive gauge fields tangent to the brane. The mass of all these fields is proportional to the separation distance between the branes. Now, if we bring the two branes together, making them coincide, this separation vanishes. All the stretched string modes become massless. The component of the gauge field pointing along the separation direction is reinterpreted as a new scalar field. Altogether, we then obtain p-1 massless gauge fields and d-p scalar fields, exactly as before. But now these fields carry Chern indices and are organized into 2x2 matrices. This matrix structure gives rise to a U2 gauge theory on the brane world volume. The scalar fields describing the positions of the branes also become matrix-valued and transform under U2 in the adjoint representation. More generally, if we bring n Dp-branes together, we get a UN gauge theory in p+1 dimensions. The gauge fields and scalar fields both become n by n matrices. This simple picture leads to a profound idea. The spacetime coordinates of the branes themselves no longer commute. In other words, string theory suggests that spacetime geometry becomes non-commutative when multiple branes are present. Spectrum of superstring theory. In superstring theory, both bosonic and fermionic degrees of freedom are present on the string worldsheet. These are governed by what's called the Raman-Neveu-Schwarz action. The theory splits into two sectors, the Raman sector with periodic fermions and the Neveu-Schwarz sector with antiperiodic ones. To remove the tachyon and enforce spacetime supersymmetry, we apply what's known as the GSO projection. In the Neveu-Schwarz sector, this means keeping only states with an odd number of fermionic excitations. The resulting spectrum of the open superstring includes a 10-dimensional gauge field and its fermionic superpartner, the Gaussiano. Both fields are massless and have 8 physical degrees of freedom. Type 1 superstring theory is unique in that it includes both open and closed strings, and all of them are unoriented. In the closed string sector, the massless spectrum divides into 4 parts: NS-NS, RR, NSR, and RNS. From the NS-NS sector, we obtain 3 important bosonic fields: the Dilaton phi, which controls the string coupling, the Kalb-Raman field B, which behaves like a magnetic potential for strings, and the metric G, which governs gravity in spacetime. The mixed NSR and RNS sectors provide the fermionic superpartners of these fields, completing the supergravity multiplet. The RR sector contains the gauge field C. These fields are crucial as they couple to Dp-branes and give them their conserved charges. In Type 2a theory, the C fields have an odd number of components, and they couple to even-dimensional branes, like the D0 brane and the D2 brane. In Type 2b, the C fields have even rank and couple to odd-dimensional branes, such as the D1 brane and the D3 brane. Type 2b also includes a scalar C field that couples to the D instanton. In Type 1 theory, the closed string spectrum is inherited from Type 2b, but modified by an orientifold projection. Interestingly, the field B, which in types 2a and 2b belongs to the NS-NS sector, now appears in the RR sector and is identified with one of the C fields. It is, in fact, the only RR field present in Type 1. Heterotic string theory is different. It includes the Dilaton phi, the Kalb-Raman field B, and the metric G, all coming from the NS-NS sector. But it contains no RR field C at all. The 5 consistent superstring theories, Type 1, Type 2a, Type 2b, and the 2 heterotic versions, are all connected through various dualities. Together, they fit into a larger theoretical framework known as M-theory, which is believed to unify them all. The NS to NS magnetic field. The Kalb-Raman field, usually denoted B, plays for strings the same role that the Maxwell field A plays for point particles. To see this, let's begin with the case of a particle. A point particle couples to the gauge field A along its world line. This is just the usual electromagnetic interaction. The particle acts as a source, and its motion generates a conserved current, the familiar electric current, which appears in Maxwell's equations. In string theory, the situation is similar, but not identical. A string doesn't follow a line, it sweeps out a surface, and it doesn't couple to a one-form field like A, but instead to a two-form field, the Kalb-Raman field B. The coupling of a string to B is expressed through an action integrated over the world sheet. This action includes the antisymmetric field B and gives rise to a field strength called H, which is a 3-form. Just like the Maxwell field strength gives rise to a conserved current for particles, the field H gives rise to a conserved antisymmetric current for strings. But here's the key point. The string is not a point-like source. It is an extended line, and its charge is not a scalar. It is a vector aligned with the string's orientation. The corresponding charge density is also a vector field, and it is divergence-free. This conservation law means that the charge cannot accumulate and the current cannot terminate. As a result, strings must be closed loops. Open strings would violate this conservation. And indeed, the NS-NS Cal-Brahman field appears only in the spectrum of closed strings. In 4 spacetime dimensions, a static configuration of strings gives rise to a Cal-Brahman magnetic field, denoted B sub H. This field arises from the field strength H, specifically from its time-space components, which mirrors how the magnetic field arises from the electromagnetic field strength in gauge theory. Just as in electromagnetism, this magnetic field satisfies an Ampere-like law. The curl of B sub H is proportional to the string charge density, a vector field, localized along the string and tangent to it. From this local density, we define a global quantity, the string number, denoted script n. It measures how many strings pierce a given surface, just as total electric charge is computed by integrating charge density over a volume. Indeed, in electromagnetism, charge is defined by a scalar density. To find the total charge, we integrate this density over a region of space, for example, a ball surrounded by a sphere. The electric field generated by the charge, the Coulomb field, flows outward through that surrounding surface. In string theory, the analogy shifts. The counterpart to electric charge is the string number, script n. And just as charge is measured by integrating the electric field over a surface, string number is measured by integrating the Cal-Brahman magnetic field around a closed loop. Imagine a circle enclosing some region. If strings pierce the surface inside, the total string number is given by the loop integral of B sub H, or equivalently, the surface integral of the string charge density. In summary, the total string number plays the same role as total electric charge in electromagnetism. The Cal-Brahman magnetic field behaves exactly like a magnetic field for strings, and it's sourced not by point charges, but by extended one-dimensional objects, the strings themselves. Gauge invariance on the Dp-brane and Rr charges. In string theory, closed strings, which include gravity, propagate throughout spacetime. Open strings, which include gauge fields, are attached to Dp-branes. Correspondingly, the Cal-Brahman field B lives in spacetime, while the Maxwell field A is confined to the Dp-brane world volume. Indeed, the Cal-Brahman field B lives in the full spacetime. That's because it belongs to the graviton supermultiplet, the spectrum of closed strings, which propagate freely throughout the bulk. In contrast, the Maxwell field A lives only on the Dp-brane. It arises from the spectrum of open strings, whose endpoints are constrained to lie on the brane. This fundamental distinction reflects their origins. Closed strings generate gravity and spacetime fields, while open strings generate gauge fields localized on branes. Open strings carry string charge, which couples to the Cal-Brahman field. Their endpoints carry electric charge, which couples to the Maxwell field. The conservation of these charges is tied to gauge invariance. For the Maxwell field, current conservation follows from invariance under the transformation. A goes to A plus a derivative of epsilon. The field strength F remains invariant. Similarly, for the Cal-Brahman field, current conservation requires invariance under the transformation. B goes to B plus the exterior derivative of lambda. The corresponding field strength H is gauge invariant. But to ensure full gauge invariance, both fields A and B must appear in the action together. The correct gauge invariant combination on the Dp-brane is not just F, but F plus B, often written as script F. This ensures that the string charge density carried along the open string is transmitted to the brane via the Maxwell field lines attached to the string endpoints. In fact, on the brane, the electric field component of F acts as a source for the magnetic field B, effectively encoding the string's presence. The action contains 5 key terms, each with a clear physical role. First, the kinetic term for the string. It measures how the string moves through spacetime. Second, the coupling of the string to the Chern field B. This tells us that strings carry B charge. Third, the endpoints of an open string coupled to the gauge field A on the Dp-brane. Closed strings don't contribute here. Fourth, the kinetic term for the B field describing how it propagates through spacetime. And fifth, the kinetic term for the gauge field A, but written in terms of F plus B, a gauge invariant combination. The cross term here shows how the string's presence is felt on the brane. Together, these 5 lines describe how strings, branes, and fields interact in a fully gauge invariant way. However, more generally, Dp-branes themselves carry RR charges. These couple electrically to higher form gauge fields, antisymmetric tensors with p+1 indices. For example, a D2 brane couples to a 3-form R field, while a D3 brane couples to a 4-form, and so on. In bosonic string theory, these RR fields are absent, so Dp-branes carry no conserved charges and are unstable. In type 2a, Dp-branes with even p carry electric RR charge. D0 and D2 branes are electric, while D4, D6, and D8 branes are magnetic, coupling to dual RR fields. In type 2b, Dp-branes with odd p are electric. D1 and D3 branes are electric, while D5, D7, and D9 branes are magnetic. These charges and the requirement of gauge invariance explain both the stability of Dp-branes and their deep role in the dynamics of string theory. Born-Infeld action. The gauge field on a Dp-brane doesn't follow ordinary Maxwell theory. Instead, its dynamics are governed by the nonlinear Born-Infeld action, which reduces to Maxwell's equations only in the limit of weak fields. In the full theory, the self-energy of point charges remains finite. This is because Born-Infeld dynamics impose a maximum electric field, a feature that emerges naturally from T-duality in string theory. The action is expressed using a determinant, the square root of the determinant of eta plus 2 pi alpha prime times F, where F is the field strength on the brane. This action is also proportional to the brane tension, denoted T sub p. But Dp-branes can also move in transverse directions. These displacements are described by scalar fields XA, which are related to compactified components of the gauge field via 2 pi alpha prime times AA. When these scalar fields are included, the action picks up terms involving their gradients. The determinant now includes both the field strength and the brane's deformations. There's also a contribution from the Chern field B pulled back onto the brane. The correct gauge invariant combination is B plus 2 pi alpha prime F, and both appear in the determinant. So the full Born-Infeld action involves the determinant of the induced metric plus B plus derivatives of the scalar fields and 2 pi alpha prime times F. If we add a background spacetime metric and a dilaton field, the action acquires an overall factor, the exponential of minus phi naught. This is the Born-Infeld action, a compact geometric structure that unifies gauge fields, brane dynamics, background geometry, and the fundamental string slope, alpha prime. The Chern-Simons action. On a Dp-brane, the open string fields, the gauge vector field and the scalar fields, interact with the closed string background fields through the Born-Infeld action. These closed string fields belong to the NS-NS sector, the metric, the dilaton, and the Chern 2 form, denoted here B2. But there is another class of interactions, those involving the RR fields, which do not enter the Born-Infeld action. Instead, they appear in a separate piece of the brane action, known as the Chern-Simons term. The Chern field B2 couples electrically to the fundamental string through an integral over the string worldsheet. Its field strength is the 3-form H, defined as the exterior derivative of B2. The magnetic dual of B2 is a 6-form, denoted B6. It couples magnetically to the NS5 brane, a 5-dimensional extended object. The NS5 brane is not a D-brane, but rather the magnetic dual of the string. It is the monopole under the Chern gauge field. Now turning to the RR sector, in type 2a theory we have 2 gauge potentials, C1 and C3, which couple electrically to the D0 brane and the D2 brane respectively. Their magnetic duals are obtained by Hodge duality in 10 dimensions, C7 and C5, which couple magnetically to the D6 brane and the D4 brane respectively. In Type 2b theory, the RR fields include C0, C2, and C4, which couple to the d instanton, the D1 brane, and the D3 brane. These fields have magnetic duals as well, C8 for the D7 brane, C6 for the D5 brane, and C4 again for the D3 brane, since it is self-dual. Here, we have implicitly assumed that the RR field strengths are harmonic. This leads to a self-duality condition between the electric and magnetic components, and as a result, the magnetic dual of a Dn-1 brane is a D7-N brane. The general electric coupling of a Dp brane to an RR field is given by integrating the Cp+1 form over the brane's world volume. However, the total RR gauge potential is defined as the formal sum of all individual forms from degree 0 to degree 8. In other words, capital C is equal to the sum of all Cn forms, starting from n equals 0 up to n equals 8. And in the presence of background fields, the Cal-Brahman 2 form B and the world volume gauge field A, the full Chern-Simons action takes the form an integral over the Dp brane world volume of C wedged with the exponential of B plus 2 pi alpha prime times F. Here, F is the field strength of A. This exponential structure means that a Dp brane couples not only to C, P+1, but also to lower rank RR forms. These are topological couplings, consequences of the geometry and gauge invariance of the theory. The Non-Abelian, Born-Infeld, and Chern-Simons actions. When we consider not a single D brane but n coincident Dp branes, the theory becomes non-Abelian. All fields now become n by n matrices, transforming in the adjoint representation of the gauge group, typically U of n. For example, in the case of a stack of D9 branes, there are no transverse scalar fields, and the total action consists of a Born-Infeld term plus a Chern-Simons term. The Born-Infeld part involves the square root of a determinant that mixes the spacetime metric, the Cal-Brahman 2 form, and the non-Abelian field strength. The Chern-Simons part describes the brane's coupling to Raman-Raman fields, again modified by the presence of the background B field and the world volume gauge field. In this non-Abelian setting, there is a trace over gauge indices. To be precise, the determinant is over the 10-dimensional spacetime indices. However, each entry inside the determinant is itself an n by n matrix. The metric and the Cal-Brahman field are multiplied by the identity matrix, while the field strength is genuinely non-Abelian. The result is an n by n matrix value determinant, and we take the trace over that matrix after computing the determinant and square root. An important consequence of the non-Abelian structure is that the Dp brane now couples not only to the usual Raman-Raman potential of degree p+1, but also to potentials of lower and higher degree. Specifically, it couples to forms of degree p-1, p-3, and so on, as well as to forms of degree p+3, p+5, and so on. These extended couplings arise from the non-trivial trace structure and the symmetrized exponential appearing in the Chern-Simons term. They reflect the richer topological structure of coincident branes and are essential in describing phenomena like dielectric branes and brane polarization. Thanks for watching this episode of Quantum. If you found this lecture insightful, don't forget to subscribe and follow the full series on gauge gravity duality and matrix quantum mechanics. Until next time, stay curious, stay critical, and keep thinking quantum.